Okay, so the next few bits of teaching we're going to do are going to be fairly brisk. We're going to try and teach a topic before the end of term, so hence the camera. So if you do miss something, or if you turn up late to a lesson, then you can always catch it on YouTube. Okay, so the first little job, I'm going to give you a carbon atom with 4 bonds attached, and I'm going to give you some things to attach to those carbons, and then we're going to see what we've got. Okay, yeah, so just to recap that, so we end up with 2 different structures which are mirror images of each other, and that only happens if we've got 4 different groups around the 2 carbons. So let's start there. We have 4 different groups around a carbon, obviously. So we use this, there's quite a lot of language associated with this. So we talk about an asymmetric molecule. It is different from its mirror. Image. So let's have a fairly simple example. If I take a carbon and let's just start by putting a bromine on it, and then if I have we'll have a CH3 over there, and then let's have an ethyl group down here. Now let's make it a hydrogen down there. There we go. So then it looks more like a bromine, doesn't it? C2H5 there. Okay. So remember when you're drawing molecules, to show their 3-dimensional structure, you need to use the wedge and the dash-shaped bond. So when we draw a molecule, you can imagine that that white one pointing up and the red one pointing to the left are kind of in the plane of the board, and then the blue one's sticking out towards you. That's the wedge-shaped bond, and the purple one's kind of disappearing off into the distance. That's the dashed bond. So that gives us a way of identifying a specific 3-dimensional structure. And then if I want to draw the stereo isomer of that, the optical isomer of that, I use a dotted line to represent the reflecting plane, and then I can put the same groups in the same places. Bromine at the top, CH3 down the side, and the wedged hydrogen sticking out towards us, but it's now a reflection of that molecule. So therefore we've definitely drawn 2 different optical isomers. Hi, question.
How come the methyl groups don't have the inner wedges?
The inner wedges?
The ones, the wedges that face away like the ethyl groups have.
I don't know what you're saying.
Oh, the you know how the ethyl groups have the dashed wedge that indicates it's like facing away. How come the methyl groups don't have that?
Right. So as I said, in this particular representation, the white and the red. So I'm sort of stick that on the board there. The white and the red are in the plane of the board.
Okay. Yeah.
The blue sticking out towards you, and the purple's disappearing off into the distance. So that's that. There are obviously other ways that you can represent the molecule. For example, I could stare at the hydrogen there like that, and then we can kind of draw a molecule like this with the hydrogen right on top of us and the 3 groups around that. There's different ways you can represent it, but this is the way that you should be familiar with and that we're going to use exclusively. in this. Yeah. All right. Any other questions? Just before we go on, I just want to do a quick family tree of isomerism, just to kind of remind you where we are. I know this came up a bit in the mock, but there's two fundamentally different types of isomerism: structural and stereoisomerism. And then there are three different types of structural isomerism, and now there are two types of stereoisomerism. Okay, so overall we've got 5 types of isomerism. Let's start with structural. Zion, can you give me a type of structural isomerism, please? Positional. Great. Could you give me some examples of 2 molecules that are positional isomers of each other? Perfect. So we could write it, or we could draw a little skeletal formula. Those are good. Matty, another type of
Chain isomerism.
Chain. Could you give me some examples of chain, please?
Hexene and cyclohexane.
Lovely. What should we do here? 1, 2, 3, 4, 5, 6. There we go. Split spot. And the last type of structural isomerism, Melvin? Could you give me examples of those? Sorry, I've just realised Matty gave the wrong answer, didn't he? Matty did a functional group isomer, didn't you? Yeah. And it was such a good functional group isomer, I forgot that you were actually doing chain isomers. So Melvin's just got to get out of jail free card. No, that's the wrong way around. Okay, it's a live show, kids. Right, so Matty is now going to give us some chain isomers.
Would a chain isomer be where the chain is different shape?
Yes.
So if I have hexane and then 1 methyl, what's that, pentane?
Not one, never 1 methyl.
Oh, sorry,
if you
2
say
methyl.
1 methyl, the methyl's on the end, it's just part of the length of it.
2 methyl.
Yeah, so if we have any kind of straight chain versus a branch chain, that's chain isomerism.
How come that's not positional isomer then?
No, it's positional if we go, 2 methyl versus 3 methyl. You could argue that's a chain isomer and a positional isomer, really.
Yeah.
It kind of fits both categories, doesn't it? But usually we reserve positional isomer for the position of the functional group. So butane-1-ol and butane-2-ol are good. Chain is when we just mess around with the carbon chain. Okay, right. What's the type of stereoisomerism that we met already that came up a bit in the exam? Can you remember? Geometric, very good. Not very often that word comes to the front. It's usually called EZ or cis-trans, but actually its correct name is geometric. So that's your EZ isomerism. So so we could have E and Z butene, which is which? You remember? Which is E, which is Z? The bottom one's E. Very good. Yeah. Okay. Which leaves optical isomerism over here. So that's our full family tree of. Sorry, I rubbed out structural there. And just to recap those definitions, they came up in the exam, didn't they? Definition of structural isomerism. Kieran, can you pull that one out of our hat?
Where you've got the same formula but a different arrangement.
Same what formula?
Molecular.
Same molecular formula.
With a different arrangement in space.
No, that's the second part of stereoisomerism. Different clues in the name.
Structure.
Different structures or different structural formula. So same molecular formula, different structural formula. That's your structural isomers. Come on, you can do the next one for me now.
Same molecular formula.
No. Well, it is the same molecular formula, but that's not the important thing.
Same structure, but
same structural formula, different arrangement of bonds in space. So, as we'll see, for example, butane-2-ol is a good example because there are two forms of butane-2-ol. All right? Butane-2-ol can have two stereoisomers. In fact, I've just changed that bromine there. There we go. I always use that as my example as well. They're both butane-2-ol. They have the same structural formula, but they have a different arrangement of bonds in space. Okay. Let's do some words now. So we already used the word asymmetric, meaning a mirror image of the molecule is a different molecule, different isomer. We've also used this slightly clumsy word, non-superimposable, meaning that the two structures can't be superimposed on top of one another. The word that's used most often, though, is chiral. So we talk about a chiral molecule, which would be one which exhibits optical isomerism. Or we could talk about a chiral carbon or a chiral center, and it's often depicted with a little asterisk. As the carbon with 4 different groups around it. Okay. There's another word that I'll come to that in a moment. There's probably a couple I've forgotten as well. The first thing we need to focus on, though, is your kind of job in the exam. One of your key jobs. Do you need one of these?
No, I was going to ask something.
Go ask away.
I saw like a video about chiral carbons. It was like they have a positive charge. I just saw something about that. I was just wondering what that meant.
Chiral carbon could have a positive charge,
Yeah.
but being chiral doesn't give it a positive charge.
I just didn't understand what that meant. I was just wondering if you knew.
Okay, without seeing the video, I can't really help you with that. But no, chiral carbons are ordinary carbons. They don't have any charge normally, unless they're reacting It's probably to do with mechanisms that make things chiral, which we'll come to. That's in a lesson down the line. Okay, if you've got your topic booklet, that one there. Can you turn to page 12? Have you not got one at all? And your first job, turn to page 12 and have a look at those molecules there. Your first job is to identify which of those molecules exhibit optical isomerism. Okay. So let's go around the class. Jacob, start with you. A, what do you think? B? C? 3. Okay, yeah. So it was my first example, wasn't it? 2-bromobutane. I've used skeletal formula up on here just to remind you that, because the questions in the exam, they're going to use a lot of skeletal formula, and you need to be familiar with them. Of course, when you look at that carbon, you see 1, 2, 3 different groups on it. You don't automatically kind of remember that there's a hydrogen sneaking away in there. Hydrogens are not shown on skeletal formula; they're just assumed. So get used to that. Eddie, what do we think about D?
Nope.
E?
Nope.
What kind of isomerism does E demonstrate?
E.
Let me ask the question. What kind of stereoisomerism does E demonstrate?
E.
E isomerism.
Well, or hang on. Yeah, geometric.
Yeah, geometric. Yeah, it could be. I've drawn the E version of that, but it could be a Z, couldn't it? F, Eddie. Yeah, we like that. Same as bromobutane, 2-bromobutane. If we've got propan-2-ol, then again there must be a hydrogen sneaking away in the back there. So we've got 4 different groups around the carbon. Jano, G.
Yeah.
So, did you do biology?
Yeah.
Great. What is G?
Amino acid.
It's an amino acid. Okay, so we will get to study amino acids in their own right, but any molecule which has an amine group on one end and an acid group on the other, an amino acid, is part of this class of important biological compounds that make up proteins. And again, we'll go into all of that. Do you know which amino acid it is?
It says that.
Oh, does it? Okay. Yeah, and I've drawn it in such a way to make it clearer that you've got 4 different groups around it. The other amino acids exist just by changing that group. If I put a different group on the top there, it becomes a different amino acid. But they're all gonna exhibit optical isomerism, except for the simplest, which would be glycine, which just has 2 hydrogens there. Of course, as soon as you've got a CH2, you can't have 4 different groups around the carbon. Okay, grand. Let's go to Kieran next for H.
I thought yes.
Which is the chiral carbon?
The first one on the propyl group.
The propyl group.
So the one to the right of the benzene.
Yeah, the one with a CH3 on it. That one there. So again, it can be useful to highlight these chiral carbons with a little asterisk. That is the convention that's used. I, Cyan? Okay. Come back to rings and things. They're interesting. And then J, which is another familiar biological molecule, lactic acid.
I thought yes.
Yeah, so you've got that chiral carbon in the middle there, and then the 4 different groups of the H, CH3, OH, and the acid group there. So for all of those 1, 2, 3, 4, 5 molecules, you should be able to draw the 3-dimensional structure of those. Yeah. Something else I was going to do and I can't remember what it was. Oh, well. Let's just pause the video while I think for a moment. Yes, right, I've remembered. Who can describe the structure of glucose to me? Hands going up. Go on, Matty.
So it's an hexo sugar, so it's got 6 carbons, so you do draw a ring with 6 carbons and the top right one changes to an oxygen.
That's right, very good.
And then you'd have on that first, so where you first draw it from, there up near CH2H5? Just CH3.
Just CH2, and
So,
then,
yeah,
because you've got 6 carbons, yeah, 1, 2, 3, 4, 5, 6.
Yeah.
And then you've got an OH on there, yeah.
An OH group, so
Start here.
so it depends which one you draw into, either alpha or beta, which one you
Okay,
want.
which one's which?
So alpha hydrogen's above, beta hydrogen below. So,
Okay, so the OH is in the opposite
Yeah.
place, so
so that would
so
be beta.
alpha is down and OH is,
And
sorry,
then
beta is up,
You
yeah.
have another OH group at the other end.
We-
You have an OH group there at the bottom, top,
You tell me.
top, bottom, top, top. It's the top, isn't it?
I think it's at the bottom.
It's on the
The
other carbon, it's on
hydroxyls
top.
can be
Hey?
On the other carbon, it's on top.
On this one?
Yeah.
Yeah,
Yeah.
that's
Yeah.
right.
And you have another OH group. down.
And this one over here?
So that'd be OH there.
Bottom.
Hold on, don't mind. Beta. Beta glucose.
It's on the bottom.
Yeah. Agreed.
Johnny's got this. Okay, right. Lovely, thank you. How many? These just H's on the end, by the way. How many chiral centers does that glucose molecule have?
2, 3, 4, 5.
I want to guess that.
Yeah.
I'm probably trying to see what most of the carbons are going to be. So one. I think it's probably less than we think. Because I said no. Like you know, it's kind of remind me of the alcohol slash alcohol. No, it's a totally different.
What have you got?
I think there's 5.
Five. It's an oxygen. So starting here, this carbon,
Yeah.
Yeah.
this one,
Yeah.
this one,
Yeah.
this one,
Yeah.
this one,
Yeah.
this one.
No.
It's a CH2. So no. So how many different forms of glucose are there? If all of those optical isomers have 2 possibilities,
50.
10.
not 50, not 10. You've got 5 coins, you're going to toss them. How many different combinations, permutations can you make? Not 25. What have you got? 2 coins? 3 coins. 32, 2 to the 5, yeah. So there's 32 different versions of glucose, possibly. How many does nature make? 2. Makes the alpha and the beta. The reason the alpha and the beta can swap, we're gonna tell me that?
I don't know the reason.
Okay, all right.
Is it like a sort of bond that forms?
Hey?
Is it like a sort of bond that forms as well? Swap.
A bond that can form.
It's
No, the glycoside
forms
bond
like a sort of bond that has to take glucose because it has to form.
the glycoside bond forms after it's either alpha or beta.
Yeah, but it forms alpha and beta because of bond.
Not because of the bond. Beta forms once it takes glycoside bonds, but alpha forms
It
once.
forms it that's because as it's grown it's already connected.
So it forms it because of alpha or beta.
When it forms it's already bonded.
It's because glucose can. This isn't chemistry, by the way. You don't have to know about the chemistry of glucose. We'll come back to the 32 in a moment. But glucose has a ring open form in solution, so it can go between the two. So, and that's an aldehyde. It has no stereochemistry, so therefore, when it goes back, it can go back to either. Okay, that's why. Anyway, we're getting off the topic here. Yes, so given that can be either, that brings it down to 16 versions. So credit to Emil Fischer, who is a Nobel Prize-winning scientist who discovered the actual structure of glucose. He also developed the style of writing bonds in a three-dimensional way with the wedged and dash-shaped bonds. That was him. And other pretty important bit of science that he did was, I can find it, there we are. He's known for this proposal of a lock and key mechanism for substrate binding, which is something we just sort of take for granted today. He also discovered barbiturates and lots of other things. So there we are. He's a clever guy. So he worked with the 16 different possibilities for glucose and managed to whittle that down to 1. Given that optical isomers are not easy to tell apart. Even geometric isomers have different melting points and boiling points, right? Because if you've got a sort of straight chain molecule versus something with a kind of big kink in it, these molecules they will stack differently, and that means you get different melting points and boiling points. So they're relatively easy to separate. But stereoisomers, optical isomers cannot be separated in that way. They can't be separated by distillation. The only way to physically separate them is by getting a dish and waiting for them to crystallize, and then you have to pick out the individual crystals of each type, which sounds like really slow, painstaking work. And that's if you've only got 2 isomers. If you've got 16 to work with, then you need a lot of patience. While we're talking about, we don't have time, do we? Okay, we'll do this next time. All right. We will. We'll come back to this. I'll just leave you with that image on the board now. Oh no, I won't leave you with that image because I've pressed freeze. I'll leave you with that image. It's a brain in a jar.